go ahead and start on practice quiz problem number 1. State the good old definition of the derivative in 2 space, what we had in calculus 1. Formal definition. Okay, 30 seconds more. Alright, so this is the limit. H approaches 0. This is one of the common ways to do it. You don't have to do it exactly this way. Of f of x plus h minus f of x over h. And this top part is representing the change in the y, and that's representing the change in the x. It's a slope. It's the instantaneous slope. And number 2. P of t represents a company's profits in millions of dollars at time t measured in years. Interpret P prime of t is equal to 46 with a complete sentence that a third grader could understand.
I'm sorry, do we type in or?
Oh, you can just write this down individually.
Oh, okay.
Yeah. Okay, 20 seconds more. Okay, if it said P of t equals 46, you would say the company's profit is 46 million each year. Profit is 46 million every year. So it's a very steady company. No matter what year it is, it always makes 46 million in profits. But that's not what we have here. We have P prime of T is 46. And so this is the company's profits increase. It's the rate of change by 46 million each year. So if it's independent of time, every single year its derivative is 46, that means every time how we interpret the derivative is the change in the output every time the input increases by 1. Every time, that's provided we stay in the tangent line. And this one is saying that it's a constant derivative. Every time 1 year goes by, the profits increase 46 million each year. Alright, and give me a little feedback on 1 and 2. Was this unnecessary review, or is this a helpful review? Where are we at on these two things? I like the way you worded that, Cameron. Each year it goes up 46 million more than the previous year. Okay. And complete the picture showing what f prime of x represents graphically. So this is my function f, and if there's x and there's x plus h, we have a definition of the derivative that had x and x plus h show graphically what the derivative represents. .30 seconds more. Okay, so what we're trying to find is the instantaneous slope at this point. This line just nicks this curve at one point right there. And we're trying to find the slope of the red curve. But what we can do is get the slope between these 2 points. And we say that that's a reasonable estimate of the slope of the red curve. Now, this point right here, if its input is x, its output is f of x. This point up here, if its input is x plus h, its output is f of x plus h. So if you gave you the 2 coordinates of this point, it's x, f of x. And this point up here is x plus h, f of x plus h. So the slope of this black line, m, is the difference in the y-coordinates, this minus this, f of x plus h minus f of x, over the difference in the x-coordinates, but x plus h minus x is just going to give you h on the bottom. So this is the expression in the definition of the derivative. And then when we move this h, we make the h smaller. The next time we do it, h is, let's say, back here. X plus h is now here. And then my second point is here. And then we get this. Then we get an even better estimate of the slope of the red line. And then we keep moving h closer and closer, and the black lines get closer and closer to the red line, the slope of that. Alright? Let me know, a little feedback. Was this review unnecessary or helpful? Alright, so that's all we had for the practice quiz today. These concepts are going to show up again today. The definition of the derivative, we're going to be extending that to a different type of function, and so we wanted to review all this stuff and its interpretation. And questions now. Any questions on 4.1 or 14.1 or anything else? Alright, if no questions, let's move on to 14.2. Calculus of vector valued functions. Alright. And vector valued functions, let's go over them again. The input is just the variable t. So vector valued functions are like this. Something, whoops. The input is a t, and the output is just a constant, while the output is a vector. So when the book uses this terminology, vector valued functions. Its input is a scalar, output's a vector. When we visualize it, we've gone over this, we tend to use this in 3 space. It's one of the only ways to get space curves. And you have to imagine only the tip of the vector leaves a mark, and that mark then maps out a space curve. Okay. And let's extend the derivative to vector value functions in 3 space and other spaces. So we could go to 4 space to 5 space, and it's real easy to extend it there. All right, so r prime of t, if f prime of x was this, then what makes sense for us for the derivative r prime of t here? And I want to just kind of open the floor. Anybody have a suggestion on how this might start out? So don't look in your book on how it goes or anything, but let's just think. If this is the derivative of a general function in 2 space, how might we extend it if this is a vector? Yes?
Yes, since each component are the functions, correct?
Yes.
So we take derivative of each functions. No?
Ah, okay. So if r of t is f of t, g of t, h of t, then r prime of t could be just what he soon is saying is, Sue is saying is just take the derivative of each one. So that's one way we could define it. Just 3 different functions, take the derivative of each one. Anybody else have another suggestion as how the derivative could have been defined?
I was thinking maybe like we had that same like kind of formula as we had for 2 space, but we kind of altered it to work for the like to fit a vector.
Okay, so how would I do that? I'd start it with limit.
Mm-hmm. And so then instead of like f of x plus h, we'd have like that vector, and then we could have like 2 times t plus h, the cosine of t plus h.
Okay, so we could have h approaches 0 still.
Mm-hmm.
And on the top is going to be, what am I going to put, the first thing?
I have like the vector, but like with like t plus h. How we have like f of x plus h is kind of like the vector plus h.
Okay,
So
how
like,
do I show the vector? What would I write for the vector?
we just do like the brackety things.
Oh, you could put them in brackets. All right. You could, like this. And then put t plus h for f and g and
Yeah.
h. Okay.
Mm-hmm.
We could do that. We could also do this. Just leave off the prime. Just like this is leaving off the prime on this. Okay. So r of t plus. Now, the one that I prefer though, instead of, so I'm going to take your suggestion, but I'm going to modify it a little bit. I like, you could use h, and h would be fine. I like just like a little change in t. T plus some change in t. Like this. Minus r of t. So we're following the format just like up here. Whatever this letter was here, it went in here. Whatever the input letter here is, it went here and here. And then on the bottom was this, because it's t plus change in t minus t, so it's just going to be the change in t down at the bottom. Okay. Now, both of these definitions could have been used. And you use either one and it'll lead to the other one. And this particular textbook, if we look up its definition of derivative of a vector valued function, it uses this one, the first one. And I've used textbooks for Calculus 3 in the past where we use the bottom definition. And it doesn't really matter. They have their choice, because if you start with this one, it'll lead to this one. If you start with this one, it'll lead to this one. Well, let me kind of demonstrate. Because what Matt was just saying was that if we wind up doing this, we'll wind up doing putting the three different components. And in the first component part would be f of t plus delta t, g of t plus delta t, h of t plus delta t, minus, and then slide this over, f of t, g of t, h of t, over delta t. And then, if you take these three limits one at a time, you take, well, you're going to have for this first part, and that's going to lead you to the f prime of t. And then you say, well, let's do the second part of this limit, which is, focus in on the second component. And that'll lead you to the g prime of t. And then you'll do the same thing with the last one, that'll lead you to h prime of t. Either way we go about it, we get it. I tend to think, when I see it in this second format though, it tends to bring me back to thinking this way, and thinking of these kind of visualizations graphically. And when I see this one, I tend to think of, oh, the derivative rules. Take, the power rule and the, quotient rule and stuff like this to take the derivatives. But either way we think of it, we're going to get the same thing.
Okay, just the idea, because each function can be very complicated looking one, right? It could be any function. So what I'm thinking is, if we treat like a limit is a whole in three functions as a one vector, and it could be quite complicated, or maybe confuses us, rather than take a derivative of each functions.
Yes, that's right. The way that you presented it right here kind of makes it seem a lot simpler. I just take it three separate functions and deal with them one at a time. And when you look at all three functions, even like the example I put up right here, they're not really nasty functions, but you can see they can be very different, But how we're going to get the derivative is whether we think of the small change in t happening and what's it's going to do. We're going to have to look at the three components one at a time. How do they all change? And winds up coming to here. So this is the way that we'll computationally work with these things. And it's much simpler. All right. And so here is the textbook's definition, the derivative. So it says R is these three different functions, and they have to be differentiable functions on some interval. And then R has a derivative, and just take the derivative one at a time. Provided R prime not equals 0, the 0 vector, R prime t is a tangent vector at the point corresponding to R of t. Now this part, this tangent vector, is going to be kind of the equivalent and an expansion of what does the derivative represent in 2 space. We're going to have a different interpretation in 3 space. Even in a 2 space vector, if it's a vector valued function. Okay. So what does it mean by tangent vector? So now we're going to explore the graphical interpretation of R prime of t. And so on R prime of t, if we had something like, so let's go in the 3 space. So R of t itself is going to map out some kind of a space curve. So let's say the space curve that it maps out is something like this. And this is my space curve. And now I'm going to have some point on this curve I'll call P. And if you froze time, so this red vector was mapping out this, that's the red vector R of t. And it was mapping out this space curve. We freeze time for just a moment right here, and we get the P. Now, a little bit later, we have a new vector. And this might be R of t plus some small amount like delta t. Okay, so very similar to the graphical interpretation over here, x plus h, t plus delta t. But we have these vectors emanating from the origin on this case. All right. So what we are going to get in this picture, this second one right here, is graphical interpretation of R prime of t comes from looking at this. It's the difference between these two vectors divided by a scalar. Now, when we take the subtraction of two vectors, That was like one of the very first sections. 13.1, we spent a lot of time in 13.1 with graphical interpretation of subtracting two vectors. So r of t plus delta t minus r of t. So we have, let me go to blue here, r t plus delta t minus r of t. We had said that, like, if you traveled from the 4-mile marker to the 10-mile marker, what's your change? That's, you remember, you go from the destination minus your original. It's a change of plus 6, 10 minus 4. So we got to go, this is destination minus starting point. So it's from here to here. Now, I should have made this curve a little curvier, because this blue arrow doesn't usually follow exactly on the green. Well, try to make it look a little different. Okay, so this right here is the change. So there's a visual interpretation of this definition right here. It's the difference between the tips. Okay. Now we're going to move the second point closer to the first, because we're going to take the limit as delta t goes to 0. So as delta t goes to 0, we move it back. And so let me actually use my eraser. Let me make a little bit better green curve on this portion. So they're distinct. Alright, so we want this to come here's my space curve, like this. Alright, so there's my original r of t minus r of t plus h minus r of t. And then we make, so here was t, and here was t plus delta t. Now we're going to take the limit as delta t goes to 0. That moves this second point closer to this first point. Maybe the next time it's going to be halfway over here. And that's going to put the second point up here. And then this is going to be this vector now. Now notice that this black vector is maybe only about half as long as the blue vector. But the delta t is only going to be about half as much. And when you divide by 1/2, it's the same thing as doubling. So the length of the vector isn't going to change much. But the direction of the vector is going to be changing more and more, because what we want is the vector that's exactly tangent to the curve. Here's the tangent line to the curve, right here. And the blue vector going to the black vector, as we move even closer, we're going to get closer and closer toward this gray tangent line. And it's going to be then the tangent vector. R prime of t is going to point in the direction that we are moving, the instantaneous direction that we're moving on the space curve. So this space curve the green vector curve, this little alien in a spaceship, flying saucer, what's its instantaneous direction of travel is going to be determined by r prime of t. And we're going to actually find out, too, that its speed is going to be the magnitude of that vector. Alright, so this, what I was putting in kind of a crude drawing, is done again in your textbook like this. This is directly from the textbook. If you have r of t plus delta t, the arrow between them, so that's destination minus starting point. That's that red vector right there. And then as you keep moving back by making the delta t smaller and smaller, you are going to get closer and closer to pushing this arrow, the red arrow, towards the tangent vector over here. So this should be very much like a three-space analogy of this kind of interpretation, and with vectors involved now. As delta t approaches 0, change in r over change in t. Now that change in t is going to be a scaling thing, and you know, as you make it half as much, the vector tends to get half as small, but then you're dividing by 1/2, which is doubling it, and it'll kind of keep that vector magnitude fairly constant. Give me a little feedback here. Does this seem fuzzy, or does this seem kind of clear as far as the graphical representation of r prime of t? Okay. And then the next idea. We have tangent vectors, which is r prime of t, and then the unit tangent vector is you just make it of length 1, magnitude 1. So this is going to be a smooth parameterized curve, r sub t. We'll talk about what smooth means in a little bit. For t between a and b, the unit tangent vector is r prime of t, but turned into a unit vector by dividing it by its magnitude. And so the unit tangent vector is a vector that's always telling you the direction of travel, but it's not telling you anything about the speed, because it's as if you're going at a speed of 1 the whole time. Okay. All right. So smooth, the smooth part, this comes here. If the magnitude of r prime of t is equal to 0, now you see, r prime of t, if its magnitude is 0, you have a problem with your unit tangent vector. You don't have a unit tangent vector at that point, because you can't divide by 0. Okay. Then the vector function has stopped. And this unit tangent vector doesn't exist. And what we say then is that r of t is no longer smooth. We don't like vector functions that stop. So you'll see many of the theorems that we have will say something like, oh, it's a smooth curve, and it'll assume that it's a smooth curve. Yes.
I have a question. Yes, so I'm not very clear about what what does the mean by smooth. Okay, the smooth curve. If it's not a smooth curve, oh, what does it look like? Is it jagged or
Okay, all right. So the graphical representation of smooth,
yes?
what you're asking? Um, the answer is I don't know. I'm trying to think about that right now. Uh, let's. The thing is generally speaking, we just say assume it's smooth, and I don't generally work with vector functions in an area where it can be zero. To make one up that could be zero, let's do that real quick. R of t is t 3t 5t. Okay, so, and this is not smooth when t is 0. Now you could say that, you say t is between 1 and 4, and then it's smooth, because it's never 0 within this. But if you did it over an interval that contained 0, then you'd have a spot where the whole thing stops. Now, what does that mean, graphically speaking? This is really some plane. Hold it, no, this is not a plane. This is a line. And 0, 0, 0, 3, 5, and then 6, 10. 2, yeah, 1, 3, 5, 2, 6, 10, so on. I think it's going to be some kind of a straight line emanating out from the origin. But it could be going in either, as long as this is the direction of travel, like this. But it's not clear from the picture that it stops at the origin, because time isn't one of these axes. So I don't think that we'll have a graphical representation of smooth. But it does present some problems at certain times, like it doesn't have a unit tangent vector, and so on. So that's why a number of the theorems will require smoothness. Good question. And all right, so let's go to number 4. And here is a problem. The figure shows a curve C given by a vector function r of t. So part A, draw the vectors r 4.5 minus r4. So just do that very first one right now. So I'm going to give you a little bit of time. Draw this vector. Okay, to draw that vector, that's the destination minus, and that's the origin point. So we go from here to here. Start, destination. Okay, and then let me give you a moment. Draw that one. So this also, destination minus starting point. Goes up like this. And now draw the vector r 4.5 minus r4, and the delta t was obviously 0.5, and so you're dividing by delta t. And draw this one, and the delta t was 0.2, and dividing by 0.2. So let me give you a moment to draw both of those. So the first one, when you divide by 1/2, it's the same thing as multiplying by 2. It just makes this thing twice as long. So let's just add the extra part to it. And this one, when you divide by 1/5, it's going to make it 5 times as long. 1, 2, 3, 4, 5. Notice its length will be pretty close to that length, right over there. The length of these vectors is getting shorter and shorter, but the magnifier is going to be bigger and bigger. Here, we get to make it 5 times as big by dividing by 1/5 over here. Okay, and they're still pointed in exactly the same directions. Okay, now part C. Write expressions for r prime of 4 and the unit tangent vector t4. And this part is kind of tricky. So go to your group chat, and I'm going to give you a little bit of time here to see if you can write an expression for r prime of 4. Now, I'll give you a hint. The expression you're writing for r prime of 4 is going to give you the exact value of r prime of 4. Exact value. And then for the unit tangent vector t of 4. Now it's going to be, what we're really going to be getting when you do r prime of 4, it's the vector that's tangent to the curve, the direction of travel, emanating from right here. See how, notice that the real thing that we're looking for is tangent to the curve, just mix the curve right here. It's this green vector. That's what we're really looking for. And as you make the delta t smaller, we're making the red vector closer to that green vector, and we get the blue vector because we made the delta t a lot smaller. And as you made it smaller and smaller, you'd be getting closer and closer to this. But now write an expression for r prime of 4, the exact value of this. And then for the unit tangent vector t4. So I'll give you a little bit of time. Okay, for the groups, as you're chatting in it, let me give you about 30 seconds more. I'm going to ask a group. Okay, group 2, you got an expression for r prime of 4?
We were all pretty stumped. The only thing I got was just like the original limit equation we had, but replacing t with 4, but that's not like a precise value.
So if we did that, it would look like what? Limit?
So the limit, you can like of delta t approaches 0 of r of 4 plus delta t minus r of 4 divided by delta t.
That is exactly what they were looking for.
Oh, okay.
Because that's the only thing we can do at this point. An expression that would give me the exact value of r prime 4. But notice what this is doing. It's kind of linking this up with the visual. This is saying, yeah, it's different now. It's not the same as what we had in the practice quiz in 2-space, that derivative. But we can still kind of be seeing this, and that, you know, when the delta t was 0.5, we actually multiplied by 2. And then when it was 1/5, we were multiplying by 5, but we're getting a constant, you know, the length is going to stabilize, and the direction is going to get closer and closer to this direction right here. All right, now, what about T4? What kind of expression might we get for T4? Anybody?
Wouldn't it just be r prime of 4 over the magnitude of r prime of 4?
That's exactly it. This thing that we got up here divided by its magnitude. Okay. And then draw the vector T4. Let me give you a quick minute. Figure out how you would draw T4. And T4 winds up being same direction as R of 4, but just 1. I don't know how far 1 unit is, but here would be T4. And this, by the way, is R prime of 4, right out here. So R prime of 4 might be pretty long, depending on how fast this little spaceship was going. But T of 4 has got this set velocity of, or yeah, velocity of 1, positive 1, in that direction. All right, so let us take a break here. We will start again 3 p.m. after a 15-minute break. And is there anybody who'd like to talk with me individually before I take my break? All right, I'll take my break. All right, start back up again. And, all right, so if this is a two-space vector valued function, and let me give you a minute, go ahead and sketch the plane curve R of t. So go to your group chat and just type in how to proceed. How do you draw the plane curve R of t in this case? And discuss that briefly. All right, so group one, how do you sketch this?
We'll start by the maker tables of each value t and x and y.
And we can put some values in like 0. So then we go -2 on the x and 1 on the y, and we make a dot right there. And we could continue doing this.
I have a question. If t's interval is not given, we just assume that it's from infinity to in the negative infinity to plus the plus infinity. So we can plug in any number we wish to.
Any number you want. That's right. But
Okay.
we'll also give you a direction because t goes from negatives to positives. Okay. All right. So what's another way we could have sketched this? Anybody?
We could have done the trick that we learned like with parametric equations, and we solve in terms of t, or solve for t and then write it as an xy equation.
So then add 2 to both sides. T is equal to x plus 2. And then every time we see that t in this equation, replace that t with x plus 2 squared plus 2. So then we see that what this is a parabola that's been shifted 2 left and 2 up. So normally it would be 0, 0, and we shifted it 2 units to the left, 2 units up. It shouldn't come down to here then.
Actually, isn't it +1? I think. Where I don't.
I'm really good at doing things like that. It's a special talent I have. So it's going to be 1 up, and so 2 to the left, 1 up. That's the vertex of this new parabola. But we do know that it's going in this direction. So these arrows appear, but there's other arrows that are direction arrows. And as t gets, like if t goes to 1, then this is -1 and 2 So it's going in this direction. Like this. Alright. And then find r prime of t. I'll give you 30 seconds to find r prime of t. So r prime of t, you just take the derivatives of these. Derivative of t minus 2 is 1, and the derivative over here is 2t. And then sketch r of t and r prime of t when t is equal to negative 1. I'll give you a little bit of time for that. On this one, r of negative 1, we just plug in negative 1 here, we're going to get negative 3. We're going to get 1 plus 1 is 2. R prime of negative 1 is we plug in negative 1 into the r prime formula. Well, the 1 is always the x coordinate, but this is negative 2 now. Now, let me show you, when you're asked to sketch r and r prime for a particular value, let me first show you how not to do it. Let's take r of negative 1, and it's negative 3, positive 2, it's right here. And then r prime of negative 1 is 1, negative 2, and it's right here. Now, open-ended question. Discuss this in your group. What would have been a better way to draw these two that's more insightful, adds insight, that's better than the way I drew these two? So discuss that in your groups. Type it up, but don't hit enter quite yet. Let everybody process this. There's, I drew the r of negative 1 up here. I drew the r prime, negative 1 down here. But there's a better way to have drawn these that adds more insight. Go ahead and hit enter. Discuss this briefly. Okay, group 2, what would have been a better way?
Well, the only thing I really thought of is we could have like continued r prime of t like kind of backwards toward the actual graph. And so like we can actually see like the slope at that point.
So, are you saying that I should move the r prime of t?
No, so just like continue like the vector backwards. Kind of extend it out.
Extend it backwards like this?
Yeah.
And how does that help?
Now that I'm thinking of it, it really doesn't.
You're on the right track, though.
I think I would probably move the origin point of r prime of -1 to the coordinates 3, 2.
Very good.
-3, 2, excuse me.
Yes, we don't want r prime of 1 emanating from the origin. Most vector functions, yes, we want it emanating from the, and it's appropriate for r of -1 to be emanating from the origin, and it should put us on the curve, and it does. It's a point on the curve. But the derivative tells us the direction that we're going and the speed. The magnitude of this vector tells us its speed. And this should be emanating from this point itself. And we go 1 over, 2 down, and we get this vector right here. And notice that that is tangent to the curve. It starts at the curve. If we move its tail there, it's tangent to the curve, and it's showing the speed at that point, right there. The magnitude of this, that we'll get into later. What we're really focusing on now is that the derivative is always tangent to the curve. Right there, and then you can see it graphically. Any questions? Okay. So we put this, don't put in standard position. Put its tail at this point. Because it tells us about our traveling when we're at that point. Okay. And we have some derivative rules. So it's same theme throughout calculus 1, 2, and 3. Whenever we do something different, we say, what are the rules in this? So we got a new type of function, vector valued functions. We define the derivative of these. So how do these derivatives work? All right, so let u and v be differentiable vector valued functions. Small f is a differentiable scalar valued function at all points t. C be a constant vector. Okay, so like we expect, the derivative of a constant vector, if the function is just never moves, it's just a vector that's constant, then it's going to give us, now notice you get a 0 vector as the result here. And then over here, the derivative of a sum is the sum of the derivatives. Similar rule for vector valued functions. And that makes total sense because we have to do them one component at a time anyway, so this is totally consistent. And then if you have a scalar function times a vector function. Now, a scalar function times a vector function, you could actually distribute the f of t into the 3 components of the u of t. Okay? And because of that, the derivative of this whole thing, you would take the derivatives of each part separate, But if you did the derivatives of each part separate, you'd still get the same thing as over here. Remember, if this was a scalar function, it's like first times the derivative of the second, second times the derivative of the first. You know, it's the same kind of thing here, it turns out. And you could verify this easily by just, you know, let u of t, since they called it f, you might want your u of t. Normally we make it FGH, you might make it H of t, I, J of t, something like this. And then you just do the f of t out in front and distribute it each one and so on. And you could verify these rules. We actually don't see these rules come up very often in our problems. So we just kind of note that these are the rules though. And then if you have a function, a scalar function inside a vector function, then we get the old-fashioned chain rule inside. The vector function just works kind of like it was a scalar function. And the derivative of a dot product, this is some kind of multiplication here. And if it was ordinary multiplication, and if these were scalar functions, it'd be first times the derivative of the second plus second times the derivative of the first. But this is some kind of a multiplication, and the analogous rule works here. And cross products is some kind of multiplication, too, of two functions. And these are vector functions now, and that is just like we'd expect with when you take the derivative of the product of two functions. Any questions here? All right. The theme is the calculus. How do you do calculus on these vector-valued functions? Well, big part of calculus is taking derivatives. Another big part is taking integrals. So we have the indefinite integral of vector-valued functions. So if r of t has three component functions, f, g, and h, and let cap r of t be cap f, where f, g, and h, where these are antiderivatives of these, then the indefinite integral. And what it's just basically saying is you take integrals one function at a time, just like you take the derivatives one function at a time. Take the derivatives of each of these separately, take the integrals of each of these separately. And then it introduces a constant c, but now it's a c vector. Three different constants, c1, c2, c3, are going to be coming up.
Would you just write that there was like one constant c? Because would those all be combined, or would they need to be written as C1, C2, C3?
You could do it either way. You could call it cap C as a vector, but it has three different, it doesn't mean that the different components are going to be identical. They can be different ones. Yes. All right. And we are going to end early today, because this finishes this section. And so, are there any questions before I stop? And the homework is, and I apologize, I should have done the homework listing it up this weekend, 14.2, but I was so busy I had exams from 3 different classes that I had to grade over the weekend that I forgot to prepare the homework assignment. So I'll prepare the 14.2 homework assignment tonight. I'll get it in tonight, within the next hour. And I'll put it up on
And
in Canvas.
14.2 will be due Monday.
So now we're back onto kind of the normal routine. So the spot check of 14.2 will be Wednesday. And then, yes, you'll be turning it in on Monday of next week. Hold it. No, it'll be Wednesday you turn in both sections, 14.2 and 14.3 of next week.
Okay.
All right. All right. You all have a good evening.
Thank you, you too.
You're welcome.
Thank you.
Thank you.
Welcome.